In part 1 on dot convention, we looked at the two different ways of winding a coil on the transformer core, the ferrite core. So essentially, the sense of winding direction decides the flex direction in the core for a given current. Okay, then let's look at what is the impact of this winding direction on the polarity of the induced EMF. Okay. So for that, let's once again consider the same ferrite transformer with two coils, and to the primary coil I apply an AC voltage V1. Okay. So that will result in, first of all, a magnetizing current in this direction, and it will produce a flex phi in this direction. Okay. So and the Faraday's law gives the relationship between this applied voltage and the flex in the core, which would be V1 equals N1, which is the number of turns in the primary coil N1, d phi over dt. Rate of change of the flex in the core depends on the applied voltage. Okay. Now the secondary coil is also bound on the same core, therefore it also completely links the flex produced by the current in the first coil. Okay. Therefore there is going to be, again by Faraday's law, an induced EMF in the secondary coil, and its magnitude would be given by V2 equals N2, where N2 is the number of turns in the secondary coil, times d phi over dt, the rate of change of the same flex in the core. Then the question is, what is the polarity of the induced EMF in the secondary coil? So let me arbitrarily define the polarity as shown here: positive at the top, negative at the bottom. But let's go ahead and determine exactly what is the actual polarity. Okay. So for that, the method we learned is arbitrarily define a current direction, okay, and determine the corresponding flex direction for this current. Okay. Now in this coil, we know that for this counterclockwise direction winding, the current entering at this point produces a flex going up. Okay. Now this flex is it has the same direction as the flex that is causing this voltage. Okay. Therefore, the current and this voltage inducing flex are consistently defined. Therefore, the terminal at which the current enters is the positive terminal. So we have defined it correctly. Okay. So therefore, the complete voltage V2, both in terms of the magnitude as well as the polarity, is given by this expression. V2 is N2 over N1 times V1. Okay. So whenever V1 is positive, V2 is also positive. So if I draw arbitrarily sinusoidal waveform for V1, let's say this is V1. Then let me use a different color here. Okay. So if N2 is less than N1, then V2 is going to be lower in magnitude, and it has the same phase. Okay. Something like that. They are in phase. Okay. So let me go ahead and consider a different case. Okay. Same transformer, two coils, but the second coil is purposely wound in the opposite direction as that of the primary coil. Okay. So once again, the V1 produces a flex phi here. They're given by this same expression. Okay. And since the secondary coil is also linking the same flex, there is going to be an induced EMF. And let me define that as V2 with arbitrarily this polarity, positive on the top. Okay. So once again, let's go ahead and determine the actual polarity of V2. For that, I define an arbitrary current I2. And because of the opposite sense of winding, the a current entering here would produce a flex in this direction. Okay. Now that is opposite to the direction of the flex phi, which is actually causing this induced voltage. Therefore, the terminal where the current is entering would actually be negative because of this opposite relationship between this phi and the original phi. Therefore, the polarity is actually positive here and negative at this point. Okay. But my arbitrary definition of V2 was positive at the top. Therefore, whenever V1 is positive, V2 with this defined polarity would be negative. Okay. So the complete expression for V2 in terms of both the magnitude and the polarity corresponding to the second case would be V2 is negative N2 over N1 times V1. Okay. So that is the impact of the winding direction on the induced EMF. So what's the meaning of negative here? It means that for the same V1, once again let me go to the same color, see the red. Okay. So in this case here, okay. So if B1 has the same applied voltage V1. Then V2 in the second case would be, once again assuming N2 is less than N1, would have a lower magnitude but opposite polarity. Okay, so that is indicated by this minus sign. Okay. So the key point is that the polarity of the induced EMF depends on the winding direction of the two coils. So that brings us to the discussion on the dot polarity. Okay. Now we have seen that the sense of winding direction matters a lot in the operation of a power converter. Okay. But in a circuit schematic of a power converter, we do not represent the magnetic components with this level of detail. We don't show the toroidal or the EE core and the actual windings with the winding directions. Okay. In a large schematic, there is no way we can represent each magnetic components with this kind of figures. Okay. So what is done is we still need the information on the sense of winding direction. So that information is given by having this appropriate dots on each of the coils. Okay. So this is how a magnetic component would be represented in a circuit schematic. This set of 3 half circles, they represent each coil. Okay, so this example has 2 coils, and this line here indicates that both of these coils are wound on the same core. They are not 2 separate inductors, but they are 2 coils on the same core. Okay. And you can notice the dots here. So they give all the information that we need about this sense of winding direction, and we can use this to determine what is going to be the flux direction, what is going to be the induced EMF polarity, and so on. So both of these magnetic components, this toroidal core or this EE core, both of them are represented by this kind of circuit representation. Okay. Now, if there is a third coil in either of the 2 magnetic components, then that would be represented by just making this line longer here and putting the third coil with the appropriate dot either at the top or at the bottom. Okay, so then we will move on to discussing what these dots actually mean. In other words, what is the dot convention that we are going to use? So there are essentially 2 main rules about the dot polarity that we need to understand. The first one is related to the polarity of the EMF or the voltage. Okay. So it says that the voltage at the dotted end of each winding with respect to its own undotted end have the same polarity. So let me explain what this statement means. Okay. So let's again consider this EE core, the transformer with this EE core and 2 coils. As you can see here, both of these coils have the same sense of winding direction. So both are wound counterclockwise, both the primary as well as the secondary, okay, as viewed from the top. Okay. Therefore, if the and we have established from our previous discussions that if the top end is positive with respect to the bottom end in the first coil, because of the same sense of winding, the top end here will also be positive with respect to its own bottom end. So if I arbitrarily put the dot at the top end for the first coil, and so whenever this dot end is positive with respect to the lower undotted end, then here also whichever is the dotted end will be positive with respect to the undotted end. Okay. Therefore here I should also place the dot at the top, so which means it will satisfy this statement, meaning whenever this end, the dotted end, is positive with respect to the undotted end in the first winding, if that is positive, it also immediately implies that in the second winding also the dotted end would be positive with respect to its own undotted end. Okay, so this complete magnetic structure can be represented in a circuit schematic as shown here. So this entire thing is shown by this figure in a power converter circuit schematic. Okay. So the dot locations give the complete information that we need about the sense of winding direction of the 2 windings. Okay. So here, the moment I see the dot placement like this and using this rule number 1, I can immediately say that whenever V1, which is the voltage of the dotted end on the primary side with respect to the undotted end on the primary side. Now if that is positive, then V2, which is the voltage at the dotted end on the secondary side with respect to the undotted secondary end, will also be positive whenever V1 is positive. Okay? And considering the turns ratio n, where n is n2 number of turns in the secondary over n1 number of turns in the primary. Okay? So V2 would be n times V1. So V2 is positive and V1 is positive. Okay? Now if the dot polarity were reversed, so for example, if on the primary side the dot is still at the top, and on the secondary side if the dot is at the bottom, and that is indicated here, so this could be representing a different transformer structure, different sense of winding in the two coils. Okay? So given this dot configuration, I can say that whenever V1 is positive, and that means the dotted end is positive with respect to the undotted end on the primary side, so that means on the secondary side will also the dotted end will be positive with respect to the undotted end, but just that on the secondary side the dotted end is at the bottom. Okay? Therefore whenever V1 is positive, the lower end would be positive on the secondary side with respect to the top end on the secondary side. Okay, so which means V2 as defined as with this assigned polarity would be negative when V1 is positive, and therefore V2 is negative n times V1. Okay? So this would be the case when, so for example in this transformer, if I remove the secondary coil and put a coil with opposite sense of winding direction, then again we can go through the analysis of the polarity of the induced EMF, and we will see that in this case when V1 is positive, it will be the bottom end which would be positive. Okay? Therefore if I were to place a dot in this figure, then I would put it at the bottom end for the secondary coil, and in a circuit schematic this structure would be represented by this symbol with the corresponding dot polarity.